As people around the world celebrating Earth Day today, let's understand how solar panels use Einstein's photoelectric effect to turn radiation that coming from the sun to electric energy. So join me to understand the physics of solar panel. So we have sun over here, the radiation coming from the sun strike the solar panel. There's a layer on the bottom and a layer on the top, and this is metal, and there is a metal on the top as well. This is a semiconductor N type, and this is P type. What does that mean? That has been doped with N type and this has been doped with P type. That means you take atom from another element, phosphorus for example, which has more valence electron than silicon, one atom, and place it on the silicon, making it doping N type. What about doping P type? You take one atom, for example, from different type of element than silicon, for example boron, which has 3 valence electron, and placing it on the silicon, making it doping P type. Sunlight strike with N type, then it can knock electron loose. So let's talk about the radiation coming from the sun first, and then we're going to talk about knock electron loose, which is Einstein's photoelectric effect. Okay. So the sun radiates, and sunlight, let's put all type of light in the EM spectrum. So EM spectrum. So we have a gamma ray, we have a X-ray, we have ultraviolet, we have visible light, we have infrared, we have microwave, we have radio wave. Okay, these are the main visible and invisible light. So we know that, what do we know? We know that the light has a speed, and light speed is 3 times 10⁸ meter per second. So we don't call it velocity, we call it c, because this number is special, it's a constant. This is the speed of light in a vacuum or in the air. Okay, so we know that this is velocity of light. We know that velocity of a car is distance over time. Is velocity of light also distance over time? Well, let's see. The light has a wavelength, is lambda, and it has a frequency f. Okay, so the d wavelength is measured in meter and frequency is measured in hertz. So distance is also measured in meter, so we can replace d by wavelength, and t is still on the bottom. So we can rewrite lambda 1 over t, and lambda 1 over t is f. Okay, so the speed of light is lambda times frequency. The sun radiates only 3 types of light: ultraviolet, visible light, and infrared. Ultraviolet, visible light, and infrared. The gamma ray has wavelength 10⁻⁻13 meters. So gamma ray is very small. So speed of light, we know that lambda times frequency. So c, if gamma ray is 10⁻⁻13, so f has to be 10 raised to what? So that this is still 10⁸ as Einstein said. This has to be 10⁻21. So yes, the frequency of gamma ray is 10⁻21. That means the gamma ray has a loss of energy. If you have a more energy, more frequency, that means you have a loss of energy. Gamma ray has more energy than X-ray, X-ray has more energy than ultraviolet. Ultraviolet has more energy than visible light. Visible light has more energy than infrared. Infrared has more energy than microwave, and microwave has more energy than radio wave. Okay. Now, let's talk about visible light. Visible light is very important for us, and they define as Roy-G beep. All right. So, what does it mean? Red, orange, yellow, green, blue, and violet. Violet frequency is more than blue. Blue frequency is more than green. Green frequency is more than yellow. Yellow frequency is more than orange. Orange frequency is more than red. We need that. And the frequency range is for visible light 10 raised to 14. Very important. So the red light cannot knock electron loose. Red light cannot knock electron loose because it does not have enough frequency. However, violet or blue can knock electron loose is because they do have enough energy, because they have more frequency. Made of atom, and atom, there are electrons orbiting around the atom. Let's consider the sun. Radiate light and strike this surface. It can knock electron loose if it is strike with enough frequency. If it strike with red light, it won't be able to knock electron loose, because those electron over here in the atom, orbiting around the atom, has a work function. What does that mean? That means the atom holding them. There is a bond between electron and atom. You have to break that bond to knock electron loose. Atom not going to say, well, come, take my electron. No, that doesn't happen. You have to break the bond to knock electron loose. And red light won't be able to do that, because red light does not have enough frequency, so it has a low energy. Get it? Work function you can think as if cost. If you have a business, for example, if you have a business, your profit is revenue minus cost. So this would be your kinetic energy. For example, revenue is the photon. Einstein called it photon. Photon means the light. So this could be your photon, and this could be your work function. So for example, if the work function is 200 joule and photon is 100 joule, then this photon cannot knock electron loose, because this photon needs at least 200 joule, need more than 200 joule to knock it loose, and it will have some kinetic energy. So if it has 201 joule, then it can knock electron loose, and that electron will have some kinetic energy. And how much kinetic energy will that have? Exactly 1 joule, because it will, a photon is 201 minus 200, so it will kinetic energy only 1. All right, so it spends 200 joule to break the bond between electron and atom, and 1 joule goes to the kinetic energy. And once it has a kinetic energy, so you know how kinetic energy turned to power, electric power. Good. This is called photoelectric effect. Einstein published this photoelectric effect 1905, and he won the Nobel Prize in 1921. Okay. All right. Now our question is, let's see if solar panel, this is the solar panel, and sun strike. Okay, we can do it here. So if the sunlight strike this n type, so when sunlight 400 450 nanometer photon strike the n type and let electron loose, that electron start moving to the p type, creating flow of electrons, which is electricity or current that light up our house. Good. Now we want to know what type of light is this. So we do need to know the frequency. How can we do that? We know that C is equal to lambda f. So we want to know frequency. Frequency is C over lambda. So frequency is 3 times 10 raised to 8 meter per second, and lambda is 450 times 10 raised to negative 9 meter. So frequency is 6.6 times 10 raised to 14 hertz. So what type of light it is? Violet. So this sunlight is violet. Yeah, violet is the one of the light sun radiate toward the earth, and these knock the electron loose. Some of the energy goes to breaking the bond between electron and atom, and remaining turn to kinetic energy, that turn to electric power. So now let me give you an example. Let's say the work function of this one is 3.06 times 10 raised to negative 19 joule. That means this photon has to spend that much energy to break this electron from the atom, so that this can knock the electron loose from the atom. So now we want to see how much kinetic energy. So energy, we know that energy is hf. H is the Planck constant. So ultimately we're going to do what we're going to do. We're going to E is equal to hf minus work function. But let's find the hf first. H is the Planck constant, 6.63 times 10 raised to negative 34 joule second, and frequency is 6.6 times 10 raised to 14 hertz. 6.63 times 6.6 times 10 raised to negative 34 plus 14 joule. So energy is 4.4 times 10 raised to negative 19 joule. Okay. Now we have to subtract it from the work function, minus 3.06 times 10 raised to negative 19 joule. Now energy, or kinetic energy, is 1.3 times 10 raised to negative 19 joule. So this much radiation turn to electricity. Not all radiation turn to electricity. Not all radiation turn to electricity. Only this much turn to electricity. Remaining radiation was involved breaking the bond between electron and atom. This was the physics of solar panel that creates, that turn solar energy to electric energy without adding CO2 to the greenhouse.